Hello, it is me once again, and this time round I want to talk about aromatic compounds. What I mean by aromatic compounds is the benzene and the benzene derivatives. So we can draw a benzene using any of these structures because the electrons are usually delocalized. So we can move the pi bond there, and that triggers the movement of the electrons to move to that position, which triggers the other one to move to that position, and you end up with the second structure. Or sometimes we just draw a hexagon with a circle inside. Okay? Now, the benzene derivatives have common names. If there's a methyl group attached, we call that toluene. If there are two methyl groups, we call it silane. But then there are terms that are specific to benzene. Okay? If we have a silane where, assuming that was the first one, and the second methyl group is one carbon away from the first one, we're going to call it ortho. So this is ortho position. When it's going to be like 2 carbons away, so like here, this is going to be in the meta position, because we say this is ortho, this is going to be meta position. Okay? And if it is like on the complete opposite side, that's going to be the para position. So with relation to benzene, we are going to encounter those terms. If we have a substituent here, this is ortho, meta, para position. Okay. Similar to the other side, this is ortho, meta, and then there's only one para position. Okay. There are other common names. We could have styrene, phenol, anisole, benzaldehyde, acetophenone. We have benzoic acid and aniline. These are common names, which sometimes are also used as parent names if there's another substituent. Like you could have bromoaniline. Okay, so we can see how we use them as common as parent names sometimes. Moving on, we know that alkenes and dienes undergo a number of reactions. For example, we've learned that when we have a diene, we can do electrophilic addition, either 1,2 or 1,4 addition. We can be able to actually reduce the diene into an alkane. Another thing we've learned is if you have a diene, we can do a cycloaddition, the Diels-Alder reaction, to form the product here. Or it could be cyclic, and we can still do the same reactions. Okay? But when we try to do the same reactions with benzene, it doesn't really undergo electrophilic addition. And if we want to reduce benzene to an alkane, this reaction is extremely slow. So it requires very high pressure and very harsh reaction conditions. So it's not really favorable. How about if we try a Diels-Alder reaction? Well, there's really no product formed. So what is really wrong with benzene? Why is it so stable that it does not want to undergo any reaction? If you want to determine the stability, we can measure the heats of hydrogenation, okay? The amount of heat released during the hydrogenation process. So if we do a hydrogenation for a cyclohexene, it produces 120 kilojoules per mole, which means if we do this for cyclohexadiene, we should expect the release of double of that amount, which is supposed to be 240. Well, 232, quite close, but not really there, which means that the cyclohexadiene is relatively more stable than we expected. Okay? Now, so we would expect that if we use benzene, it should be able to produce 360 kilojoules per mole. So we expect the amount of energy produced to be much higher. Now it happens that the amount of energy it produces is only 208 kilojoules per mole. So it is really stable, more stable than we expected. There's a difference, an actual difference of 152 kilojoules per mole. So this compound is more stable than expected. Now, in the next video, I'm going to talk about how to classify the aromaticity of compounds. Thank you for watching.